Hello. So back in Chapter 2, we used the van der Waals, SRK, and Pang-Robinson equation of state to calculate the compressibility, then ultimately molar volume of a fluid at a given temperature and pressure. And so back in Chapter 2, I shared with you MATLAB code to perform such calculations for you, and there was also a screencast in Chapter 2 to demonstrate the use of this code. So now in Chapter 5, we're going to build upon this to additionally compute our residual properties using a cubic equation of state. Okay, so in this screencast, I'll share with you a sample code to calculate the, in addition to molar volume, residual enthalpy and entropy using the SRK equation of state, and then we'll demonstrate its use with example 5.10 in the text, and we can also use example 5.10 to verify the correctness of the code. Okay, and so here is a function I've created, VHS SRK, which is essentially just an extension of V underscore SRK, which we used back in Chapter 5. So in looking at the function signature, so the function name has changed just to indicate that I'm also going to return enthalpy and entropy. But otherwise, the inputs are exactly the same. So temperature, pressure in bars, omega, so eccentric factor, critical temperature, and then pressure in bars. And then in terms of variables being returned, so now I've just added to the list HR and SR, the residual enthalpy and entropy. Okay, but otherwise, everything is exactly the same. And if you want, you could take a look at the code to see exactly how things work. But essentially, the equations are provided for us for HR and SR in the text. They just require first calculating Z, which we did back in Chapter 2. So the example that I'll demonstrate is I've created a script to kind of facilitate sharing this example with you to demonstrate use of the code. And so we're going to look at example 5.10 in the text. Okay, and so if I flip to 5.10, okay, well first I have example or table 5.3 up. And so again, when it comes to calculating residual properties, all of these expressions are already worked out for us. Okay, and so we can just take those expressions as is. Okay, so 5.10 is very similar to the example we considered back in Chapter 2. So if my memory is correct, back in Chapter 2, we verified our code looking at computing the molar volume of saturated ethylene at 260 Kelvin, and the pressure was 30.3 bars, I believe. And so here we're asked to look and calculate residual enthalpy and entropy of ethylene at 250 Kelvin and 30 bars using SRK. Okay, so it's at a lower temperature at the same pressure, so it's going to be a compressed liquid. So we'll take our liquid-like route, but otherwise everything is virtually exactly the same. Okay, so they give us values of the constants, which I use to help troubleshoot my code to make sure it's working. They give us values of the three compressibilities. Okay, then since we have a liquid, they're going to choose the smallest root, and that's what they would go and calculate HR and SR with. Okay, so how the code works. Okay, so this example will demonstrate how to use it, and you could save it and modify it for your problem of interest, or just call the function directly from the command window if you're comfortable with doing that. Okay. But all I've done is I looked up the critical constants and eccentric factor in the back of the book for ethylene and assigned those to variables. Okay, this is exactly the same as our Chapter 2 example. So now in terms of temperature and pressure, okay, so we need to specify T and P. So this problem, our temperature is 250 Kelvin and pressure is 30 bar, and we're told that this is a compressed liquid. Okay. So then how we would go about the calculation, right? An example functional call would look just like this. Okay, so we're going to call our function VHS underscore SRK that we just looked at. Inputs are going to be temperature in Kelvin, pressure in bar, eccentric factor, critical temperature in Kelvin, and critical pressure in bar. Okay, and we're going to assign the outputs to a laundry list of variables. Okay, and so it's the same as in Chapter 2. We've just added 2. So molar volume, which will be in centimeters cubed per mole. Residual enthalpy, which will be in joules per mole. Residual entropy, which will be in joules per mole Kelvin. compressibility, which is dimensionless, and ideal gas molar volume in centimeters cubed per mole. Okay. So just as in Chapter 2, Z could either be a scalar. You could return... Okay, so remember, if I have... these are cubic equations of state, so I can get up to 3 real roots. So in my code, I filter out the imaginary roots and return all real roots of Z. Okay, so Z can be a vector up into length 3. Okay, then V, H, and S, right, can also potentially be vectors. So what I've done in the code is I just take all of the Z's, all of the real Z's, and compute molar volume for all of those Z's. Then same thing for HR and SR. And so when we run the code, we'll see all the values of Z, and then it's up to you to identify what phase you have and to then choose the appropriate value of SR, HR, and V. Okay, the values of Z will be ordered, okay, and the values of SR, HR, and V will be ordered so that, say the first element of V corresponds to the calculation with the first element of Z. Okay, and so you can match up the terms and use that to identify which value you want. Okay, and again, volume centimeters cubed per mole, HR and SR and SI units, joules per mole and joules per mole Kelvin. In this laundry list, okay, if I don't want to return all the variables, right, so say I don't want to delete or return V ideal gas, right, I could just delete it from the brackets. Okay, but I'm going to return everything for now, just for the sake of demonstration. Okay, so this is called example 510. So to test it out, okay, I'll just call it as example 510. Okay, and so I have it displaying everything. So in this case, we get 3 values of V, 3 values of H, 3 values of S, 3 values of Z, and then there's V ideal gas. Okay, so if I look at Z, we have a compressed liquid, so we're going to want our smallest Z value, which is the 3rd root in this case. So in terms of entropy and enthalpy, we'd want the 3rd value. Okay. So now a point of confusion that actually came up in Chapter 2 is this notation used by MATLAB. Okay. So when it returns the results for HR, SRK, so the residual enthalpy, we have 1 times 10 to the 4 times blank line and then this vector. Okay, what this means is each one of these elements is multiplied by 1 times 10 to the 4. Okay, MATLAB's trying to express everything using a common factor so it can display it as an order 1 type of number. Okay, and then there's volume as well, right? So the 3rd one's the smallest one. Okay, and so what you can do is if you want just the 3rd value, okay, and that scientific notation business confuses you, these are all vectors. Okay, so if I want just that last one, okay, I can type Z underscore SRK 3, right, and I'll just get the last value. Same thing with HR, okay, in parentheses 3, right, I get the last value and negative 1.0388 times 10 to the 4. Okay, compare that to the answer in the book. All right, it's an exact match. If I want SR, right, same thing 3rd, I get negative 37.6224, all right, which is an exact match in the book. Okay, so great, excellent. You could do the same thing with volume, right? We already checked to make sure that works back in Chapter 2. If you wanted to reduce output, so say I didn't want to return Z and V ideal gas, right, I could just delete those, and now if I were to run it, all right, now I'm only going to get S, H, and V. I'm not going to get your value of Z. Okay, but my recommendation would be include Z because we'll use Z to identify the appropriate root and then the appropriate value of HR and SR and V to ultimately use. And you can get rid of V ideal gas if you want. That's not such a big deal. Okay, and if you're not comfortable with MATLAB, you can just keep resaving copies of this script and update it for your problem of interest. Or if you're a little more savvy, I'd imagine you can just copy and paste parts of this, or just call your function directly from your command window. Okay, but that's SRK. If you wanted to, and so SRK should be completely sufficient for our homework problems. If you wanted to look at Peng-Robinson or van der Waals, right, we would just start with our Chapter 2 homework, and then to modify van der Waals, right, here's the two expressions for HR and SR. Okay, again, notice they're dependent on Z, and so what it would be is we would take our code from Chapter 2, calculate Z, and then once you have Z, you can go and calculate HR and SR. Then same thing with Peng-Robinson. We would just take our code from Chapter 2, you would calculate Z, and then once you have Z, okay, we can go and calculate HR and SR. Okay. You'll notice for SRK and Peng-Robinson, we have this additional term, dA dt, the derivative of A with respect to t, which is required when we work out such expressions for cubic equation of state. But it's nothing more than just another parameter, which we can just calculate outright because we know t, and then plug that in to those expressions, right? So, extension to Peng-Robinson and van der Waals is rather straightforward. It's just a matter of being careful to make sure that you type everything up correctly and you get all of your parentheses just right, right? And so, for example, when I was solving or writing this code, I accidentally misplaced this right parentheses over here, so the numerical result was off, right? And that's where comparing to the book was great because it allowed me to check to make sure that my code was correct. Okay, but hopefully that gives you enough information to help you solve for residual properties using the SRK equation of state, and give you some insight to extend this to van der Waals and Peng-Robinson if you'd like.